We're going to talk about another way in which we can get interference, perfect constructive and perfect destructive interference. We could have waves from multiple sources being emitted and get interference that way, depending upon how those waves meet up. For example, if we had two speakers, if I had two speakers and they were both emitting, they have to emit identical waves in order to get perfect constructive or perfect destructive. But if they were both emitting identical waves, depending upon how they met up when they reached you, you may hear a really, really loud spot, which would be a perfect constructive interference, or a dead spot, which would be perfect destructive interference. So it's interference due to waves traveling further than another. If you remember, when we talked about the wave equation, we said that this term was called the phase, which is phi. When we have superposition, when we have more than one wave at the same time, we simply are going to add these wave equations. Now, again, we're going to look specifically at identical waves. So they're going to have the same amplitude. They're going to have the same wave number, because they're going to have the same wavelength. They're going to have the same angular frequency, because they're identical. X1 and X2 represents how far into the medium the wave has traveled. So if I have two speakers, let's say I have a pole, and I have a speaker down low on the pole and a speaker up high on the pole. So I have a speaker down low, and I have a speaker up high. Both are emitting sound in every direction, but let's say we're over here listening. Now I know sound is a longitudinal wave. It's a bit challenging to draw longitudinal waves, so I'm going to draw it as if it's transverse, just because that's easier. So we have this wave being emitted coming to us. This one's emitting the same wave, but this one has farther to travel. So by the time it gets to us, it may not have the same phase as the first one. Does that make sense? So ultimately, what we hear, whether we have a point of perfect constructive interference or perfect destructive or somewhere in between, is ultimately dependent on how these two phases relate. The difference between the phases, the delta phi, the phi1 minus the phi2, determines whether or not we get perfect constructive, perfect destructive, or something in between. For example, I have two waves. If the phase difference between them is 0, that means they are in phase. What does it mean to be in phase? How do I need to line these up to make them in phase?
The peaks and the valleys need to match up.
Right, so the peaks need to be right above, right on top of each other, the valleys right on top of each other. So like that. So if this is 0, we'll get perfect constructive interference. But is that the only time we can get perfect constructive interference? Is there any way to adjust the top wave and still have them be in phase?
They could be 180 degrees out of phase, or pi radians.
pi would be only half a cycle.
Oh, so that would cancel out. No,
Yeah. So how do we get back into phase?
360.
360, or 2 pi. If I shift this, sorry, it's kind of hard to shift. I could shift it a little bit and still have peaks lining up and valleys lining up. That is a phase shift of 2 pi. So we can say 0, or it could be 2 pi,
Or multiples there.
or it could be 4 pi, or it can be 6 pi. So some multiple, exactly right, some multiple of 2 pi will allow these to stay in phase. Okay? So if we take these two phases and subtract them, because we have the same wave number, I can factor that out and I'll get x1 minus x2. T1 versus T2. We live in a world where time is set. We're not looking at things happening at different times. We're only looking at the time the waves reach us. T1 and T2 are the same. So when we take T1 minus T2, we're going to get 0. So the term where we're subtracting these guys is going to give us 0. Phi naught is the original position, basically. The original phase shift of the wave. So we can say K times delta X plus delta phi naught is equal to some multiple of 2 pi. We're going to look at a couple instances. This delta phi naught, it's 0 if the waves are in phase when they are emitted. For example, with this example of sound, if the two speakers are emitting identical waves, we're implying that they are emitting them in phase with each other. So delta phi naught would simply be 0 in a case like that. Delta phi naught is pi if the waves are out of phase when they're emitted. So we would have to have the two speakers emitting exact mirror images of each other. The one wave would have to be going up while the other wave went down. So this equation, delta x, represents the extra distance one wave travels compared to the other. So, going back to this example with sound. These two speakers are emitting identical sound waves, so delta phi naught will be 0, because their two sounds are in phase as they are emitted from the speakers. Let's go ahead and modify this equation a little bit. In place of k, I'm going to put 2 pi over lambda, because I know k is 2 pi over lambda. Delta x represents the extra distance one wave travels versus the other. For example, this wave travels a distance of x1. Using a little geometry, we could figure that out. This wave travels a distance of x2. Are x1 and x2 the same? No. So delta x is simply x1 minus x2. How much bigger is x1 versus x2? Excuse me. Delta phi naught 0. So this has to equal a multiple of 2 pi. Turns out the 2 pi's cancel, and we find that delta x is equal to some multiple of a wavelength, which should make sense. We come back to this example. Get these guys to move. We said these guys can be in phase as long as their peaks line up. So they could line up perfectly like this, or I can shift it down so this peak lines with this peak, and so forth. This would represent the extra distance. How much of a wavelength is that? Peak, a valley, all the way back up and down, back to a valley. How much of a wavelength is that? It's a whole wavelength. But I could pull this over and line that top peak up with this one. So now that's the extra distance. How many wavelengths is that? 2. And we can keep going. As long as the extra distance one wave travels is exactly a whole integer wavelength, then we're going to get perfect constructive interference. Now technically, m can be 0 in this equation. What would m equal 0? What type of situation would that represent?
Perfectly in phase.
It would be perfectly in phase.
Or they both start at the same time. No difference in distance.
There's no difference in
Same-
distance. So they
same
both
margin.
traveled the same distance to get to the observer. So that would be us like standing smack dab in between them, along a line in between them. Both waves would have to travel exactly the same distance to get to us. Okay. So 0 just refers to no extra distance traveled. 1 would be the extra distance being equal to exactly a whole wavelength. 2 would be the extra distance being equal to a whole, 2 whole wavelengths, and so forth. Okay. In terms of sound, this would be a particularly loud spot. So you could be asked to find the first loud spot where the sound is particularly loud. Okay. What about perfect destructive interference? So that they cancel. We know they have to meet up, so one of them has a peak when the other one has a valley in order to get destructive interference. How much of a shift in radians is that? Pi. So if we come back up here, we can say phi1 minus phi2 needs to be an odd multiple of pi. It can be 1 pi, 3 pi, 5 pi. We can't say m pi, where m being any number, because 2 pi would take us back to perfect constructive interference. So an odd multiple of pi, basically, let's jump all the way to the end. How much of a wavelength is that? To get them to line up where the peak is at a valley. Half a wavelength. So we can say, falls out from this equation. If the extra distance is some multiple, odd multiple of half a wavelength, so that we always get a half, or 1.5, or 2.5, 3.5. To write that in terms of m so that we can use the same m values, we can say that delta x needs to be some quantity m plus 1/2 times the wavelength. This gives us perfect destructive interference. M, writing it this way, m can also be 1, 0, 1, 2, 3, and so forth as well. Okay. So it all boils down to the extra distance traveled. How much one wave travels further than the other. If they are in phase, Okay, as a side note, please remember these two equations are specific to when delta phi naught is 0. So that means the waves are in phase to begin with. Okay. It all boils down to how much farther one wave travels versus another. So for example, let's say our speakers are 1.5 meters apart. Let's say this lower speaker is at ear level, so the sound that's coming horizontally out of the speaker is what's coming to our ear. If this particular position so this position happens to be the second soft or quiet spot that we hear. So as we walk along the ground, the sound's going to get really loud and then really soft and then really loud and then really soft. And that's because if we keep walking, we're going to alternate between these two positions. Now granted, if delta x is something in between m lambda and the quantity m plus 1/2 plus lambda, you're still going to hear the sound. It's still going to be interference. It just won't be perfect either way. So you'll hear, when you pass through a point where it's particularly loud, that's a perfect constructive spot. If you keep walking away from the speaker, you'll pass through a point where it's really quiet. If you keep walking away from the speaker, you'll get to another point where it's loud again, soft again, loud again, soft again. Does that make sense? So let's say this particular position right here, right now, is the second soft or quiet spot. That's supposed to say spot, sorry. That we reach. What I'd like to know what is the frequency of the sound? So what frequency are the speakers emitting? Now the only way you can get perfect constructive and perfect destructive is if the waves are identical. So if you're at a concert and you go walking around, these loud and soft spots aren't really obvious because you have a whole bunch of different frequencies being emitted. Okay. You get interference, so it doesn't sound as nice in some spots as others, but you won't get the nice perfect ones. Okay. If this is a soft or quiet spot, which situation are we experiencing? Constructive or destructive? Destructive. So we know delta x is n plus 1/2 lambda. Second, that's going to refer to our m value. What is the second possible m value we can have? 1. The first soft spot would be m equals 0. The second soft spot will be m equals 1. So we're going to simplify this. Delta x will be m plus, so 1 plus 1/2, so 3/2 lambda. So lambda will be 2/3 of delta x. So let's find delta x. Delta x is the extra distance one wave travels further than the other. This top wave is traveling farther than this bottom wave. This bottom wave is traveling 4 meters to get to us. How far is this one traveling?
4.3.
How do you find that?
Pythagorean theorem.
Pythagorean theorem. So 4 squared plus 1.5 squared, square root. So that wave is traveling 4.3 meters to get to us. So delta x, the actual difference in the distance one wave travels, 4.3 minus 4.3 meters. So this particular wave traveled 30 centimeters further than the bottom wave. So 0.2 meters is our wavelength. And we're not quite done. The problem didn't ask us for the wavelength, it asked us for the frequency. But that's easy enough. If we have wavelength, how do we find frequency?
Divide velocity by the wave.
Exactly. Frequency is wavelength, speed over wavelength. So 343 meters per second over 0.2 meters.
17, 15 meters.
So about 17 meters.
Per second.
Oh, sorry. Hertz.
No, that's 1,715. 1,715.
Gotcha. 15.
Yes, 1,715.
I'm sorry. I apparently need hearing aids.
Gotta love English. You have just 10 ways of saying the same thing. They're all pretty ridiculous.
I was interpreting a decimal place in there. My problem. So 1,715 hertz, or cycles per second, is the frequency of this particular sound. By the way, too, just as an FYI, sound in terms of frequencies we can hear, normal hearing is between about 20 hertz to 20,000 hertz.